record, darn it. We'll go into this in more detail soon, but if the slope is not constant, we're going to need calculus to figure that out. What is the rate of change for that function? And pretty much the whole class is going to be involving that idea. It's just going to be applied to many things, but in essence, that's what the derivative will be. And that is, in order to get a derivative, you need to use limits. So limits define your derivative, and then derivative will allow you to find out things about rates and also maximums and minimums, etc. So it's going to be applied to many different things. And it becomes very useful in physics and engineering, that whole idea of derivatives, which we're going to talk about nonstop this whole semester. But anyway, that's the main idea as to why we need calculus here versus up there, because this is no longer a simple function. The rate of change is no longer constant. Okay. Here's another example. This is more of a calculus 2 type of question. But the concept you can see, right? Part A, you can use geometry to find the area of the shaded region. Do you agree with that? You could figure that out, right?
Yes.
But now look at this shape. That's no longer a basic geometrical shape, is it? Like over here, you can use all kinds of formulas, right? On this guy. But here, I'm like, well, maybe you can approximate, right? Like a rectangle and then kind of try to guess that or estimate. But exact area is not going to come from geometry. Geometry can approximate, but you're going to need calculus on part B to get the actual total area here. And that's when calculus 2 shows up and helps you do integration. But you see the difference when the questions are basic, you don't need calculus, but when they start to get weird, you have to use those ideas. Does that make sense? Like why it matters? And of course, we're not going to go too deep into this. This is just some basic example as to why you need this, not exactly how it works. Because these number 5 and number 6 is concepts from calculus 2. So the idea, which we were not going to go into, but just for fun, if you put an infinite number of rectangles underneath here with an infinitesimal thickness, it'll become smooth. That's what they're talking about here. So the more rectangles I put, the more fit underneath, right? You see how they start kind of like getting smoother and smoother the more I put in there. So if I put an infinite number of them, then I get this perfectly smooth shape like this. So calculus uses this idea of summing an infinite number of rectangles to find the area. That's why we need it here versus over here. Here it is not necessary. Here we need it. But anyway, so 2.1, I just want you to read the section and think about those concepts. I'm not going to actually, we're not going to go into these rectangle ideas until calculus 2. So if you're not going that far, you don't have to worry about it, but just look over the concepts. Okay. There's not much work to be done here. I'll let you work on this on your own. I'm hoping you've already started doing it or finished it, but if not, it's okay. 2.2 is when we actually start getting to work, and we need to start understanding the idea of limits. So if you didn't today, but what I want you to do from now on is look over the section, look over the notes in the book, and then once class starts, I'm going to show you how to do this and how it works. Okay. I'm not going to spend the entire time telling you what's in the book. I'm just going to show you, okay, how do I solve this? What am I doing here? That's what we're going to focus on. So I want you to make sure you at least look through the book to see the theory, write down the formulas, and then show up here to solve problems. Okay. That's how I'm going to do this. But I will add theory when I can. because sometimes you guys, I know some people might not read it, but let's do number 1 here. So first of all, in case you didn't read it, let me just briefly explain what a limit is exactly, or how you find one. Let me see, let's pick a rando function. Maybe this one, I guess. Alrighty, was x minus 4, is that what it was? I already forgot. Let's check. Yeah, x squared minus 5x plus 4. Okay. So here's the function in question. You guys can see the graph, right? I'm switching between tabs. I assume you can see the tabs. Can you guys see this graph?
Yes.
Okay, thanks. So to make sure I'm not talking about something you can't see. Okay, so they want us to find the limit. So this is how you read this. The limit of this function, they want to know what is happening as x approaches 4. So in plain old English, this question is asking you to do is to look at the function as x approaches 4 from both sides. The left side, see how they're getting closer and closer to 4, but they don't actually plug the 4 in. The plug-in number is really close to 4 on the left side. Left meaning below the value, the negative direction. And then the right side, meaning the positive direction. They're getting closer and closer to 4. 4.001, 4.01, etc. See how that's almost there, right? And they're plugging these values into this function, and they're trying to see what is the number that it's approaching from both sides. You see that? So they're both approaching the number 0.333. So all you got to do is get your calculator and plug these numbers into here. And then you just keep going. And then you'll find out what they're approaching. But this is the main idea, right? 4 was the number. Okay. So here's 4. See how the function is technically undefined? So if you plug in actually 4 in here, you're going to get division by 0 or an indeterminate form, meaning 0 over 0 or infinity over infinity, something weird like that. You can't really plug in 4. If you were to look at your table on the calculator, it's going to show you as well, undefined. So since I can't plug it in, what you do is you approach from the right side. So I'm getting closer and closer from the right. And I want to know, what is the y value? What is the function doing? The functional value as I get closer and closer to 4. So look at that y value. You see how it's getting closer to 0.33, right? Right, 0.3. And then from the right side or left side, same thing. I keep plugging in numbers closer and closer to 4, and I get 0.33. I see how it's getting, it's almost there to 3.3. See what I'm saying? See what's happening? So the idea of a limit is I can't plug in the value, but I can see what's happening from the left and right. You know, if the values from the left and the right are approaching the same thing, then you say the limit exists. So the limit exists in this example, and it's going to be 0.3333. Okay, so this is just you plugging in numbers, nothing crazy. But the concept is this. I'm approaching some value from the right. I'm approaching 4 because that's what they said, right? They said that right here. As x approaches 4, what is the function doing? Well, it's approaching this number. And by when I say what is the function doing, I'm talking about the functional value, the y value, the output values. That's why we're plugging them in here and here. We want to know, what is the output? What's the output? Does that make sense? Do you see the main idea of a limit? See what they're trying to do? So these are coming from the right. These are coming from the left on the graph. And we looked at that picture just a moment ago. Any questions on number 1? Does that make sense? There's not much to really work out by hand. This is all an idea. Okay. So everyone understands the concept on number 1.
Yes, it makes sense.
Okay. So number 2 is the same deal. You're approaching from the left and the right. And you're trying to figure out, okay, well, what's happening to the number? And your calculator is going to give you numbers closer and closer to 3. The answer is 3 on this one. So that's what you should see when you're punching these into your machine. You should see as my function approaches 0, as the x's approach 0, the y value, the function outputs 3, the closer I get to 0. Okay. So that's all you're going to do. You just plug in numbers and then see what it approaches. This one's a little different. Notice how as you plug them in, this one's negative and this one's positive. So that should be a hint. I'm like, okay, well, if I go from negative to positive, 0 is going to be in the middle, right? This has to be 0. And it makes sense, right? When you think about it. Do you see how you would punch this into your calculator? These problems. Okay. Well, let's do one that's graphical. It actually gives us a picture. These are, I think, pretty straightforward, right? You just plug in the numbers and see what's happening. You just write them down, whatever. On this one, on number 5, this function right here, I want you to answer, let me know what the answer is. This is the f function right there, 3 minus x. This right here, let me write that a little better. This, oops, over that 2. This is f of x. Okay. So what is f of x doing as the x's get closer and closer to 2? Here's the 2. What is the function approaching? From the right side, from the left side. What's happening to y? What's happening to the function?
Is it getting closer to 1?
Yeah, you can see right here. as the x's get closer to 2, it's getting closer and closer to 1, right? Because this point right there is the point 2, 1. So as I get closer and closer to 2, the function is going to 1 from the left side and the right side. That's why the answer, the limit, right, is going to be 1. In this case, the limit is equal to just plugging in the number. You can't always just plug it in. You should try. That should be the first thing you do, is just plug it in and see what happens. If you get a number back, then that is the limit. But the concept is what's important, though. You know, I'm pretty sure everyone here can plug in a number. Who cares about that? The concept is this, right? I'm approaching a value from the right side, the positive side, all the way to go infinitely close to the number in question. In this case, 2. Infinitely close from the left. Does that make sense? Do you see what they're doing?
Yes.
That's why the limit is 1. Any questions on number 5? All right, cool. Number 6. This one, check this out. The functional value is out here. It's not defined here, is it? There's a hole there. So let me zoom in a bit. I can. It's a little better, right? Where's the question at? Oh, here it is. So they're telling, so this is f of x. It's a piecewise function. Do you guys remember piecewise from college algebra? And they just broke 2 functions into 2 pieces, or that I should say they glued 2 functions into 1 function. This function is made of 2 pieces. Piecewise function. That familiar? Okay, I'm assuming that's a yes. All right. So this is f of x. As the function gets closer and closer to the number 1, right? What is the y value doing? What is the y value approaching as the x goes to 1?
If it was a closed circle, wouldn't it be approaching -1? But because it's open, the limit does not exist.
Well, the function doesn't exist at 1, but the limit does exist. So the limit is going to be -1. So because I'm getting closer and closer to -1, but the function is not defined there at 1. It's telling me that it's equal to -2, right? It's over here. So in this case, the functional value is not the same as the limit. Like on the last one, remember how it was the same?
Yeah.
Plugging in 2 gave me a 1, but the limit was also 1. Over here, the limit is -1, but plugging in 1 gets me a -2. So the functional value doesn't have to exist. But the limit can still exist even if the function is undefined at that location. Okay. So just look at the picture and say, okay, what am I approaching? Or is it the same from both sides? And if it is, the limit exists. -1. That's how you're going to put -1. Any questions on number 6? So far, not too bad. Just let me know, because I can't tell if it's super hard or super easy. You gotta tell me. Okay. Number 7. Well, let's go to -4 first. I think that's right here. So from the right side, right, the limit from the right is a +2. The limit from the left looks like, I'm sorry, I think that's, let me rephrase that. I screwed that up. Well, the limit from the right is 1, right? It's going through 1 right here. From the left, it's going to, it's approaching -1. You see how they're not the same from the right and left? If it is not approaching the same thing from both sides, then the limit does not exist. So you do have a thing called single-sided limits. But the actual limit doesn't exist. So what you would write, right? This is the notation. I think it's in the next section, but the limit of f of x as x approaches -4 from the right side, the positive side. You agree that that is equal to 1, right? The limit from the left side as x approaches -4, you would put a minus for left side. You see how that's equal to -1. When these are the same, you say the limit exists, right? You would put the answer here. But since it's not the same, you say it does not exist. So this limit does not exist. The single-sided limits do exist, but when they are not equal, you'd say the actual limit does not exist. Does that make sense?
Yes, that makes sense.
And there's definitions in the book. They'll tell you the actual requirements for existing and not existing, but that's the main one. That's all you gotta remember. There's different from the right and left. Does not exist. So you tell me right away. Do you think this one exists? Like by looking at the picture, as x goes to 0, what is the left-handed limit? What is the right-handed limit? What do you guys think? So I approach 0 from the right. What would be my answer? Approach 0 from the left. You don't see it. See from the right side, the y value is going down to, it stops right before, right? It's approaching. Yeah. 0 from the right and 1 from the left. Exactly. So now that you found the left and right sided limits, does the actual limit exist?
No.
No, because they're not the same, right? So you just put simply, it does not exist. Does that make sense? That's how they got this here. So graphically is, I think, the best way to see it and understand it is doing the graphical approach. So whenever they give you a question like this, just graph it and see what's going on. Okay. Like same thing here. Pi over 2 is right there. Once you graph it, you can see right away what's happening on the left side and the right side. You can see that as I get closer to pi over 2, it goes to infinity, shoots off, and from the right, it goes to negative infinity. So they're not the same infinities, different infinity. So does not exist. Anyway, does the main idea make sense? I'm gonna leave the rest to you. It's the same thing over and over again. So maybe a little more difficult at the end, but same thing, same concept. Any questions about finding a limit using numbers numerically or graphically? Is that doable? Do you see what a limit is?
Yes.
Okay. All right. 2.3 is finding limits analytically instead of graphically or, numerically. All righty. These I might have to do on, well, maybe I might have to do this on paper. Let's see. All right. So as I said before, this is 2.3, right? Yeah. No. 2.3. So as I said before, first thing you should try is just plug it in and see what happens. -3 cubed gives me -27. Right? -3 times -3 times -3 gets me this. The fact that I plugged it in and nothing bad happened, no undefined, no error, means the limit exists right there. If you were to graph it, you would just go with this location and you would get this y value. So you could visualize it with a graph. You can just plug it in analytically and see what happens. Or you can plug in numbers getting closer and closer from the right and left side, like we did that first example. So those are 3 different techniques to find a limit. There's using numbers close on both sides, using a graph, and then using your algebra skills, which we're going to do in this section. But first things first is just plug it in, right? If I plug in a 1, you see that I'm just going to get 1 over 1 plus 2. So I get a third. The fact that this exists, I have no issues. The limit is a third. Nothing crazy, right? That makes sense? So you're just going to plug in the numbers and see what happens. Number 5 is when we got to do some algebra to help us out. We're actually going to have to work this out. Let's do 5 on paper. Find the limit. So the limit as x approaches -3 of x squared minus 9 over x plus 3. Do you see what would happen if I plugged in -3 right here? What problem would we have?
It'll cancel out.
Yeah, the -3 and 3 would cancel, right? You get a 0 down here. We can't have a 0 in the denominator. So you see how I can't just plug it in and move on, right? But what you can do is use algebra and see if you can cancel factors. Because the top part, you agree, is a difference of squares, right? Because in a factor like this, these will cancel, leaving me with this last term here. Does that make sense? Now notice at this point, you can just plug it in, right? Without having problems. Once you plug it in, that means you're taking the limit. You no longer have to write the limit symbol. And that's it. That's your answer, -6. That's how they get this here. If you were to graph it, you would see that the y as x approaches -3 from the right and left, you're going to get closer and closer to -6. So you can still use the techniques from the last section. You can still use graphs if you want. Okay. This would be the same type of deal. You're going to factor the top using the difference of cubes. It's going to cancel. All right, you're going to end up with what? That'd be x minus 1 times x squared plus x plus 1 over x minus 1 as x goes to 1. These will cancel. So you just plug in the 1 into here. These x's here, I should say. So the limit as x goes to 1 of x squared plus x plus 1 is going to equal 1 plus 1 plus 1, right? Anyway, you see the idea here, right? Use algebra to change the question, change the function where you are allowed to plug in the number. That's what they're doing in this 2.3. Is there any questions on 5 or 6? Not too bad so far. So that's all you'll do here. Number 7 actually forces you to show every single step. So you factor the bottom, you cancel that term. See what they're doing. Here is the same thing as before. You just need to use different factoring techniques. Number 9, you have to use conjugate pairs. Do you remember using conjugate pairs? Let's do number 9. Oh, it's weird. Find the limit. Okay. So the limit, square root of x plus 6 minus 3 over x minus 3. So whenever you see a square root like this, you should think, okay, I need to use conjugate pairs. I mean, you could try plugging it in, but you should see right away. Plugging in 3 will give me a 0 on the bottom, right? So to do this algebraically, you're going to have to multiply by the conjugate on top and bottom. The conjugate is always going to be of the part that has a square root. So this right here is multiplying by the conjugate. We're basically forcing a difference of squares to happen because that'll square both of these terms. Okay. So the difference of squares formula tells us that when you multiply a conjugate, a plus b times a minus b, you're going to get a squared minus b squared every single time. So right here, you're going to get this thing squared minus this thing squared. Okay, so this will become x plus 6 minus 9, right? Over x minus 3 times this garbage. X plus 6 minus 9, that'll give us x plus 3, right? Oops, sorry, it's not on the camera there. Dang it. So these will cancel, and I get to here. So at this point, you can finally plug in the 3. So that'll give me square root of 3 plus 6 plus 3, which is 1. 3 out of 9 is 3 plus 3 is a 6. So the limit will be 1/6. So this type of technique is called multiplying by the conjugate. So if you see some weirdo square root thing on top or at the bottom, multiply top and bottom by the conjugate of this term. So if you have a minus, use the plus version. If you have a plus, use a minus version. That'll force the difference of squares to pop up here, which gets you to there, which then lets me cancel terms and take the limit. Any questions on this example? Problem 9. Okay, let's move on to something else. Number 10, 11, and 12 are formulas from your book. So basically, there's a formula that says when you take the limit of a sine x over x as x goes to 0, so if you have a sine x over the x as x goes to 0, the formula says this will go to 1. And you can prove this by using the squeeze theorem or the sandwich theorem. But if you just remember this fact, you can solve these questions. So you can just factor out the 1/3, right? If you look at this question right here, if I go factor the third out, you see that I'll have this formula, right? So this part goes to 1. That's how they get a third. Just use this formula here, which is in your book. Over here, it'll be the same. Just simplify the numerator. Sine, cosine, and tangent will cancel out, giving you just a regular sine. And you'll end up having do some algebra, and you'll end up using this formula here. Okay. You have any questions on 10 or 11? Do you see how you would use the formula? Okay. So yeah, pretty much 10 through 14, I mean, it's going to be that same formula. You just might have to get clever with your algebra. But in essence, it's the same thing over and over again, the last few. Okay. Anyway, let's see. As far as syllabus, so the main thing I wanted to do today is 2-1, 2-2, 2-3. So on Thursday, I'm going to do 2-4, 2-5, and then I'll leave some time for homework questions. So I'm hoping by Thursday you'll get stumped on some of these. And if not, great. That's awesome. But if you do, Thursday would be a good time to bring some questions. As far as lecture, we'll stop here. Do you have any issues? Because I've noticed only a few people have got into the homework. Anyone having issues getting in the homework? Do you know how to get there? Well, I know we did that together, but I think I only saw 3 people enrolled, so it's kind of concerning. Well, I have 5 now. That's good. So I only have 5 people. So if you're not one of those 5, let me know if you need help getting in there. So there's 8 people in this class. All right. I'll see you Thursday then. If you have questions, just stick around for a bit. And if not, I'll see you Thursday.